Hello everyone. I want to talk today about these things, IGBTs. Now, I see a lot of things out there that say you can do cool things with these IGBTs, but a lot of people really don't know actually how to use them the right way, and they end up with something like this. And how split open that is. But today I want to show you the right way to use one of these things. Now, an IGBT, first of all, is a transistor. It's an insulated gate bipolar transistor. That's what it stands for. But what is that really? Now, that's very similar to a Mosfet driving the gate of a bipolar junction transistor. A bipolar junction transistor has superior on-state conductivity, but a Mosfet has a gate that's very easy to drive. It doesn't take much current to turn a Mosfet all the way on. So somewhere along the line, somebody was obviously thinking, what if we combine these devices? A device with a gate that's easy to turn on, but also superior on-state conductivity. Okay, so if you don't know how a Mosfet works, if you Google or YouTube Mosfet tutorial or transistor tutorial, it'll pretty much teach you everything you need to know about a Mosfet transistor. And once you understand that, you can understand an IGBT fairly easily. Now, a lot of things that people get hung up on are the gate of the IGBT. So you have a couple terminals here. Now this is a dual IGBT module. It's got two of them in it, so it's got two gate terminals. Now the gate is what triggers on the IGBT, just like on a Mosfet. Except the gate on an IGBT is a little different because it has an extra capacity. The reason it has capacity is because of the physical size of these things. So they have a conductor that is insulated by an insulating layer, because the gate, again, it is insulated. So that means it's a capacitor, and you have to charge up that capacitor before the gate comes fully on. Now you want to switch the IGBT on very quickly, because when the IGBT is only half on, then it's acting like a resistor and not a conductor. And that's bad because that means heat. And heat blows things up like that. So you need to have a properly designed gate driver. And that's another thing that people get hung up on, is the gate driver. What kind of gate driver should I use? What current rating? What gate resistor? Well, it tells you in the data sheet. Now the IGBT that I want to show you working is an MG100Q2YS1. Says in the data sheet that I have here that it should use a 9.1 ohm resistor. Now if you use Ohm's law, you can find out what kind of current you need. It's just 15 divided by the resistance, because the gate is 15 volts as suggested by the data sheet. And data sheets vary depending on what IGBT that you want to drive, but usually it is 15 volts. So if you have 15 volts divided by 9, I don't want to sit here and do the math, but 2 amps should be fine for this. So you know that you have to have a 2 amp gate driver to drive this thing the right way, and you know that you need to have a 9 ohm resistor. Now, what's the deal with the resistor? Well, since the IGBT's gate is a capacitor, that means that the gate driver is going to have to fill up that capacitor. And as you know, capacitors have low resistances, so you need to put a resistance in, otherwise the gate driver is going to be overcurrented and it will blow. And the other important thing about IGBTs, they switch fast and they switch inductive loads. So that means that they have to have a way for current to get out. Why? Because when you switch an inductive load, a magnetic field builds up around it. And when you switch off that load, then that magnetic field collapses. And that means the current is looking for a way to get out. If you use Ohm's law again for voltage, voltage is current multiplied by resistance. So if we have a high resistance, then the current won't get out very easily. There'll be a high voltage, and that will break down the IGBT because it will exceed the IGBT's blocking rating. So what they've done with these IGBTs, they've built in a recovery diode. So that way, when the inductance switches off, the inductive load can flow out through the diode, but that doesn't mean anything if it doesn't have something to go into. So that's why you need a capacitor bank to store that energy when the IGBT switches off. But not only do you need a capacitor bank, you need a low inductance capacitor bank, because inductance also acts like resistance when there's a high switching frequency. So that will also build up an impedance and impede the flow of that current. So you need to make a bus that has capacitors enough so that it will store that and it will accept it, and also with the bus bars very close together and very close to the IGBT. So there's the least impedance possible. So when that IGBT switches off, that current will flow into the capacitor bank with very little voltage because there's very little resistance to it. Now keep in mind, when that happens, you have a capacitor bank with a very little resistance, and that's very dangerous. So you want to be careful around that. So now you understand a couple things about these IGBTs, but there's still a little more you need to understand about them. Voltage saturation, or voltage saturation across the collector and the emitter. Basically, an IGBT is a conductor, or it blocks. It blocks or it conducts, but it's not a perfect conductor. So when you probe it across the two terminals, there's going to be some voltage there. And if you don't understand that, think of it as like one of these things. Current shunt. Okay, if you know how that works, the current rather flows this way, and you get a voltage that comes out of it, and the higher the current is, the higher the voltage will be coming across these two terminals. And then you hook your ammeter to that, and you can read how much current's flowing. Well, an IGBT is like that, sort of, because when it's conducting, again, it's not a perfect conductor, so there's going to be a voltage across it. Now, in the data sheet here, they specify that this particular IGBT has a saturation voltage of 2.7 volts. Now, why do they call it saturation? Well, that's because when the IGBT is truly in its full conducting state. And like I said again earlier, it's bad when it's not in its fully on state or fully off state, because then you'll get a higher voltage, and that means you'll get heat, which makes things go boom. Now, isn't that crazy? Look at how badly I've blown that thing apart. So, you know the gate acts like a capacitor, and you have to fill that up quickly, but you don't want to fill it up too quickly because you don't want to blow your gate driver, so you need the proper gate resistor to go with it. Now you know how to use a gate driver and how to select the proper resistance for it. It shows you in the data sheet, and you know what saturation voltage is, and you don't want to exceed that saturation voltage because, again, the IGBT will explode. And you know that you need to have a low inductance capacitor bank. Well, now it's time to show you a little demonstration with an IGBT. Okay, this is a little assembly that I've made. You can see I have a capacitor bank, and with the capacitor bus bars really close together, and I have the gate there hooked up with the gate resistor, and we have a timer and a gate driver and an isolated power supply to run those. And also we have a load, a water heater. I have this set up for pulse width modulation. So the average power is going to be modulated by the pulse width, or the average time that the IGBT is on. So what I'm going to do is charge up this capacitor bank, turn everything on, and show you what happens with pulse width modulation. power supply. Circuit breaker's on. Now we're going to pre-charge the capacitor bank through a resistor, because otherwise we're going to get a big inrush current if we just connect it directly to the rectifier. So we're going to pre-charge now. Charging up. This does take a little while. I have some rather high resistance resistors for this. That looks about good. Now we're going to connect it to the mains now. Now, I'm going to change the meter a little bit. I'm going to hook it to the collector of the IGBT to see voltage that we're going to get. So right now it's off. The IGBT is blocking. And what we have to do to turn it on is increase the pulse width. And we get about 32 volts there to the load, which is 15 ohms. But you can turn it up I don't know what pulse width that is, maybe 80% of pulse width. And see what our load is up to over here. And it's starting to bubble in there. But that should give you a pretty good idea of how to use an IGBT appropriately. A couple of other considerations. The gate driver, you want to have a good capacitor to supply the power, because it does need to dump out a good bit of power into the gate to make it switch on. You want to keep those leads short and as close to this thing as possible. And safety too, when you want to get the bus bars close together and short, and you want to be careful you don't drop anything over that, because they can be very dangerous. You don't want to touch them either. It will really give you a good shock. Where is my meter at? Go. This isn't the best pulse width modulation circuit, but it holds pretty steady. Let's watch it just for a bit. I don't know how that water gets so dirty.